Hi, this is Miriam,
And this is Hale.
and this is our presentation on the self-organization of aphid colonies in Apache network. So in our study of aphid populations on yucca plants emerges important ecological concepts. The overarching framework from which our study is based is population dynamics, which is the understanding of how and why populations change in size and structure over time. The factors involved in such studies are per capita birth and death rates, as well as migration and extinction rates, and importantly here, predatory-prey dynamics. One fundamental concept belonging to this category of ecology is the Turing pattern formation, which discusses the observed pattern of diffusive instability in which there is an activator, which is the prey, and inhibitor, the predator, that can coexist by creating an ordered structure out of random chaos. This we will demonstrate in our graphical analysis. Additionally, observed from our data, we have bistable states, or in other words, two stable equilibrium states, with either very large aphid populations in some patches and very few aphids in the other organized patches. This leads us to our research questions, which are, what are the population dynamics of aphids and ladybugs on yucca plants? And what factors are causing the bistable states of aphid populations on yuccas in the study site? So to give some context to our data, we point to Professor Kummel's collaboration with Professors Brown and Bruder of the mathematics departments here at CC on their published study from 2012. In the interest of spatial self-organization of an ecological system, Kummel, Brown, and Bruder chose to study how might predation drive self-organization of aphid colonies on yucca plants. The study was conducted in an 18 by 32 meter study area in a contiguous yucca stand of Sunderman Park in Colorado Springs in late May to late June of 2007. The spot was chosen for its uniform topography and the presence of only one type of aphid species and one type of aphid predator. In a 30-day period, the researchers observed the patchy habitats of aphids on 107 yucca plants.
Okay, so for this presentation, we analyzed two different experiments. The first monitored changes in aphid populations on yucca plants that were surrounded by cages, and the second experiment analyzed changes in unprotected aphid populations, as well as the varying population of ladybugs in the same area. For the caged aphid populations experiment, 11 yucca plants were surrounded by cages made of wood and aluminum window screening, which allowed access to the yucca plants for the aphids and ants in the area, but prevented ladybugs from predating on the aphids. The quantity of aphids on each plant were counted daily for 30 days, which allowed for accurate information on the population dynamics of the aphids without any predation, due to the fact that these cages were never breached over the course of the experiment. Additionally, there was only one species of aphid present in this area. And this data was then compiled in Excel, where scatter plots are made showing the development of the aphid population over time. After this, the R value, which is the per capita growth rate of the aphid population, was calculated over the course of the 30 days. This data was then compared to the population measurements to determine how the per capita population growth changed over the measurement period. And this experiment was specifically done in May of 2010. The unprotected aphid population, as well as the ladybug populations, were recorded in late May and late June of 2007. Aphid and ladybug populations were recorded on 107 different yucca plants and in this 18 by 32 meter plot of land. This plot was located within a 56 hectare yucca stand, as we mentioned before, in the city of Colorado Springs. Similar to the previous study, this data was collected over the course of 30 days, where the aphid and ladybug populations would be counted on each yucca plant for every day of the experiment. It was then also compiled in Excel, where scatter plots of population and metapopulation versus time are created.
So on to the results and our graphical analysis of our data. This first graph simply shows the per capita growth rate of, or R, of aphids over the 30-day time period for the caged aphid plants. This was done by calculating the natural log of the percentage increase between consecutive days. The blue line here shows an exponential increase up until it flattens out before the population hits around 3,000 aphids, which we presume to be the aphid carrying capacity. The red line representing the aphids R value shows a general downward trend, and the spikes show that some aphid patches were reaching high population densities while some patches were not. This initial graph leads us to believe that there is potentially a potentiality of a dual state system within the aphid patch network, in which aphids can exist at low numbers and at high numbers on the yucca plants when there is no risk of predation. And again, this next graph also just simply shows the per capita growth rate of aphids, demonstrating that as aphids start nearing around 3,000 in numbers, their growth rate tends to decline. We believe this is due to the natural carrying capacity of the aphid population, since this is the data of aphids in the controlled conditions of the caged yucca plants where there is no predator presence. This thus eliminating any predator-prey dynamics and pushing us to assume that the aphids will move out from a patch when they reach their population limit.
These three graphs above show the changes in aphid population in the second experiment. But yeah, changes in the aphid population that can occur due to predation from the ladybugs rather than being in a cage. The first graph in the upper left, which is data from plant 9, which is the number plant it was out of 107, depicts a large spike in aphid populations early on the data collection period, implying that predation from ladybugs is occurring later on in the data collection period. The graph of plant 69, which is in the upper right, shows a period of low population in the early part of the experiment, but a large spike in aphid population occurring later in the data collection period. The graph of plant 97, which is on the bottom, shows that the aphid population increased rapidly during earlier parts of the experiment and then drops slightly, but recovers to the higher levels seen previously. This can be directly related to diffusive instability and the biostability of the aphid population. The high population of aphids results in the ladybugs migrating to the aphid's location, which causes drops in population due to the predation in the area. In certain scenarios, the aphid population is able to recover from the ladybug predation, but will dramatically decrease in others. Once the population becomes low enough, the density of ladybugs will decrease as well, resulting in the aphid population beginning to grow again. This pattern of predation creates islands of aphid populations that are large in population, but also results in the areas surrounding these islands being almost completely devoid of aphids. This results in biostability in the ecosystem, where aphids can either exist in very low or very high quantities on yucca plants. Diffusive instability is exemplified in this graph as well, comparing the metapopulations of aphids and ladybugs. The blue line, which represents the aphid population, increases initially, which is followed by a spike with the orange line, which represents the ladybugs. The ladybugs in this scenario are attracted to the aphids, who are acting as activators when their population is higher, which then results in the predation experienced by the aphids to increase. This aphid population then decreases and the ladybugs have less food than was available than before, causing ladybugs to leave the area and allow the aphid population to recover. The aphid population, in summary, attracts the ladybugs, who then inhibit the population and population growth of the aphids, causing both aphids and ladybugs to leave or be removed from the area. For our last graph, this graph shows us the R value, specifically between days 11 and 12 on the plants, and that's on the y-axis, compared to the natural log of the aphid population on day 11. The points where the trend line crosses the x-axis are points of equilibrium, while attractors at around 2.5 and 8.8 for the aphid population, and a repeller at around 6.9 for the aphid population. The two attractors are separated by a repeller, which proves that there's biostability in the ecosystem. This first attractor at 2.5 aphid population equals an aphid population with about 12 individuals if you take it out of the natural log, meaning that this attractor is acting as a refuge point for the aphids when at low populations. The higher attractor, around 8.8, is the carrying capacity, which, when converted back to an actual population rather than the natural log, would equal a population of about 6,600 aphids. This means that the populations below the first attractor will be able to grow above the refuge point, while the larger populations will have to struggle to reach the carrying capacity due to the high amounts of predation by ladybugs at higher aphid populations.
So for our concluding remarks, our analysis focuses on the dynamics of aphids and ladybugs based on the theoretical framework of Alan Turing's diffusive instability due to the observations made from our data analysis. After observing the existence of two stable states of equilibrium present in various data collections and our graphic interpretations, we attempted to understand why there is such variability, pointing to patches of large aphid populations and patches of small aphid populations, and why they increased or decreased in size, and how come they organized as such. Turing's theory of diffusive instability points us to the explanation that the aphids, otherwise known as activators, and the ladybugs or inhibitors work to coexist in a system that fluctuates from large population patches of aphids, then preyed on by ladybugs, overall resulting in population dispersal, and the fluctuation then continues. Significantly, this study provides evidence of bistability states in the predator-prey dynamics of the studied aphids and ladybugs.